Okay, so this is the 2006 AP Physics B number 5. Um, so what we have here is another PV diagram, pressure volume diagram, and if you look at the arrows, they're going in a different way than usual. We'll see if that comes into play here. It says a cylinder with movable frictionless piston contains an ideal gas. Remember, all gases that we deal with will be ideal, so that doesn't change anything. Contains an ideal gas that is initially in a state 1, which is at 1 times 10 to the 5th Pascal, 373 Kelvin, and it has a volume of 0.25 cubic meters. The gas is taken through a reversible thermodynamic cycle as shown in the PV diagram. So the object starts at 1, progresses through 2 in an isobaric process, then goes up to 3. We can't assume that that's isothermal. We'll have to check and see. And then this last final process is isochoric or isovolumetric. So part A says calculate the temperature of the gas when it is in the following states, state 2 and state 3. So if you look on the right here, we've got all of our given information, and I even included the graph for us so we can have that to look at. So if we look at state 2, that's the one on the far right, and we're going to try to find the temperature there. Well, what you want to do is you want to take a state that you know a lot about, which if you look, we know the temperature, we know the volume, and we know the pressure at state 1. Well, let's use that to find the temperature at state 2. So what we're going to use is the combined gas law. And we're looking for T2. Now, it'd be helpful if there was anything we can cancel, and in this case, it's an isobaric reaction. Isobaric means that pressure doesn't do anything. So if you look at state 1, it's at 1 times 10 to the 5th, and at state 2, it's at 1 times 10 to the 5th. So you can cancel that out. But don't worry, if you forget or you don't realize that, you still get the right answer. So now we plug in our volume at position 1, which is 0.25, our temperature 1, which is at 373, our volume at point 2, if you look at your given information over here, is 0.5, and T2 is what we're looking for. Once you run through the calculations, you end up with 746 Kelvin. There's your final answer. Okay, so what we're going to do is the same thing at state 3. If you look at state 3 right here, if you look at state 3, you see that state 3 and state 1 are related by the constant volume between them. So what we're going to do is we're going to set up a relationship just like we did here. Only instead of 1 and 2, we're going to look at 1 and 3. Now, we just said that the volume remains the same. So, in this case, we can take out the volume and make that red. And we're left with P1 T1. P1 over T1 equals P3 over T3. You just plug in your information. At P1, I know the value. And because of room here, I won't write it out. But when you break down and solve for temperature 3, you end up with 560 Kelvin. Okay, so it's a good thing we said before that 2 and 3 isn't isothermal, because if you look, the temperatures are not the same. Okay, so moving on to part B. Part B says calculate the net work done on the gas during the cycle. Now, this on the gas, by the gas thing is going to be a consistent thing. You really got to keep track of that. Now, remember, there's a couple ways to do this. You can use work is equal to negative P delta V, or you can find the area of that triangle right there. And the formula for a triangle, the area of a triangle, is just 1/2 BH. The base in this case is this distance right here, which is 0.25. And the height in this case is this distance right here, which if you look is actually 50,000. It's the difference between 1.5 and 1 times 10 to the 5th. If you're not sure, you're not confident about your conversions, you can just leave it like that. Okay, so now when you plug all that into your calculator, and what you end up with is And the sound cut out, but you can see you end up with 6,250 joules. Okay, moving on to part C. Part C asks, was heat added to or removed from the gas during the cycle? And then you have to justify your answer. Okay, so this is really going to be a hang-up for a lot of people, so I'm going to try to give you some tips here. The correct answer is heat has to be removed from the gas during the cycle. Now, the shortcut, the tip is, I told you, or I mentioned in another problem, that if the area going to the right, so if you look over in the bottom right of the triangle here, this area right here is the whole thing, right? And you have to subtract this area, and what you're left with is just the amount of work done. Well, if the yellow is bigger than the green, well, how about this? If your arrow is going to the left, you see in your triangle right here, the arrow is going to the left. That means that heat, well, what that means is positive work. Well, if this is a reversible cycle, that means the change in energy has to be zero. Our first law equation says it's Q minus W. Well, that means in order for this to work out, heat has to be removed from the system in order to keep that to be absolutely zero. Because we're doing positive work here, heat has to be removed in order to keep internal energy zero. But this is a nice handy tool if you don't like the first law explanation. Basically, if your triangle goes counterclockwise, that is going to be positive work. If your triangle goes clockwise, that's going to be negative work. Okay.